Okay, class, good afternoon. This is the video for the Tuesday, September 22nd class. Today's Monday, September 21st. And we're going to just be doing a short video today covering epitaxy and starting on lithography, particularly electron beam lithography. And okay, so starting on epitaxy, this is where we left off last time. And I'm going to be handing out homework when I upload this video. And the homework will be on epitaxy as well as e-beam lithography. And one of the things I want you to understand from this chart is that various semiconductors have a lattice constant and a band gap. The band gap determines the optical and electrical properties of the material. And so, for example, you can grow on a gallium arsenide substrate you can grow layers of aluminum arsenide and gallium arsenide. Okay, because they all have a lattice constant, as you can see on the chart there, and I'll refer, to avoid the camera going out of focus, I'll use my little marker here, because they both have a lattice constant about the same, about 0.563 or so. And so because they have the same lattice constant, you can grow one on top of the other, and everything is fine. The aluminum arsenide is just happy because it's at the same lattice constant. So if you look at what's happening on a crystalline basis, here's the gallium arsenide on its lattice. Okay, and so the aluminum arsenide, forms on the same lattice, etc. And then the gallium arsenide starts to form on the same lattice, etc. So you see, it's like as you do epitaxy, it's the same crystal all the way through. It's just that when you do a layer of aluminum arsenide, the atoms are different, but it's on the same crystalline lattice. And so, that's very, very nice. Now, I'm going to cover another case that we talked about last time, which is that if I do silicon, okay, and then I do germanium, all right, now, this is not a happy situation because, all right, silicon is on a narrower lattice. So here's my silicon atoms on its surface. All right. Now germanium, as you can see, has a larger band gap. So it wants to be spread out more. All right. So so it kind of wants to bond like that, but it can't. And so what happens is that the first few monolayers of germanium that you put down, well, they conform to the lattice. Okay, they're like, okay, we want to be spread apart more because we have a bigger lattice constant, but we'll go ahead and we'll make our best here to try and fit in there in this silicon lattice. And it's being scrunched up. It's not happy. It's really, really unhappy because it wants to have a bigger lattice constant. It wants to be like this. All right, so what happens is that, okay, for a little while it's like, okay, I'll keep going like this. I'll keep going like this. It's trying, and then after a certain distance, it's like, no, I'm sorry, I'm not doing it anymore. And so it goes, to the lattice constant it wants to be at. And so what happens is that, well, okay, so here's my lattice starting out, all right, and it's basically starting out strained. That's the word for it. It's under strain, it's under pressure because it wants to be bigger, but it's tying itself to this small silicon lattice, and so it's really unhappy. And you know, it can keep going like that for a while, going on that lattice. And it's like, okay, you know, and then what happens is, oh no, I'm sorry, I want to be like this, okay? All right, and you can see what I just did there. All right, it like said, okay, no way, I'm done with this. I want to be on a bigger lattice, and so look, it left those two, and they're like, oh, they're no longer part of the lattice, and that's called strain relaxation. It's basically where if you try to grow something with a different lattice constant, it's happy for a while. It can do it for a while, but it's under so much strain as it goes thicker that at some point it's like, no, no more. Okay, I'm going back to my normal lattice constant. I should have drawn this one this way. Okay, so now up here it's back on its normal lattice constant. And so what happens is it goes on the small lattice, you know, for a while, and then it says, no, I'm done. And it basically breaks, and it leaves these guys here. And now what are these guys here? They're defects, right? Because they're imperfections in the crystal. So instead of having a perfect crystalline layer, you have a defected layer. And that's germanium. Now what you can see, though, is that it can keep up with this for a little while. And there's a chart here. In the book. The kind of now this chart is versus germanium contact. Now we haven't talked about alloys yet, so we'll talk about that in a little bit. And what this chart is showing is that the critical thickness, that's basically, well, there's sort of a gray area in here, but below this line, it's like, okay, it will conform to the lattice of the substrate. Above this line, it will not, above that thickness. And then in between, it's sort of a gray area. Just think of it that way for now. Now, if we go back to, now let's start talking about alloys. All right. We go back to our main chart here. One of the main purposes of this chart is to teach you what alloys do. Now, for example, what's a good alloy here? I'll write it down. Alloys. Okay, an example of an alloy is indium X gallium 1 minus X arsenide. So that's X indium arsenide plus 1 minus X gallium arsenide. So it's like a mixture of indium arsenide and gallium arsenide. And what happens is that, okay, if you look at it, let's say X equals 0.1. So basically it's gallium arsenide, gallium arsenide, you know, going on here. Arsenide, gallium, well, that's not the way it goes, just do it this way. Arsenic, gallium, arsenic, gallium. And then what happens is that every once in a while, one of those gallium atoms is replaced with indium, 10% of the time. So when a crystalline alloy is a single crystal, it's just that there's a percentage of one or the other type of atoms that's replaced with the other part of the alloy. Now, if you look then at your chart, and I chose a bad example, but it is the homework problem, because for some reason this chart doesn't have a connection here. see, here's indium arsenide, and there should be a line going to gallium arsenide, which for some reason they don't have on this chart. I apologize for that. But basically, it'll do something like this, which means that if I have 10% indium, it's over here somewhere, and 100%, 90% indium, it's over here somewhere. Now, what I want you to do is to treat the lattice constant of the alloy. So the lattice constant of indium gallium arsenide, for example, is X times the lattice constant of indium arsenide plus 1 minus X times the lattice constant of gallium arsenide. Meaning, just use a linear approximation, which usually is pretty good for that. All right, so now let's get to silicon germanium. So silicon germanium is here. Here's germanium, and here's silicon. And so they have a line here which shows what silicon germanium does. That basically, as you add more germanium, it moves to a higher lattice constant, something in between. So what we can do here is we can replace this picture with silicon germanium. All right, and just treat silicon germanium as another crystalline material, having a lattice constant and having a band gap along that line there. And then going back to this diagram here, what it's showing is that depending on how much germanium is in there, okay, it tells you how thick a layer you can grow and still be stable. So for example, if it's silicon germanium with just 10% germanium content, you can grow, and this is a log plot, so going up here, that's somewhere around 30 nanometers. So you can make it 30 nanometers thick before you have to start worrying about it. And if you exceed 1,000 nanometers, then for sure it's relaxed like I've shown. And so kind of obviously, the more germanium you add, the higher the lattice constant will be. And so the lower the thickness you can do. So, so basically, what this is showing is that, now let's imagine we only make that layer this thick. And so we're still below that strain limit. All right? And so that silicon germanium has held together. It's like, okay, I'm hanging on to this silicon lattice. I'm okay. And then you stop it, and then you start growing silicon again. And it's like, oh, okay. So I have this layer of silicon germanium, and then I just start doing silicon again at its lattice constant. And this is not the scale. There's more than one monolayer there. But the point is that you have silicon, or you have a silicon substrate that ties your lattice constant. You grow silicon germanium up to a certain point below the strain relaxation limit, and then you start growing silicon again. And since you started growing silicon again, it's holding that whole thing together now. And so you don't get any defects. And as long as this is below that thickness, okay, you have a single crystal. So this is a very important called heterostructure, and as mentioned, this is when you take if you've taken ELEG 446, 646, or when you take it, you will learn that this is how you make a bipolar transistor using heterostructures, where this is the emitter, this is the base, and this is the collector, and you'll learn why that's important. So the lessons here are that when you do epitaxy, the band gap has to be the same But if you grow a layer thin enough with a different, I mean, the lattice constant has to be the same, but if you grow a thin enough layer below that relaxation limit, which is determined by how big that lattice constant is, it will stay together as a single crystal. And this layer in here will be strained, but it'll hold together. All right, and that's the basis for BiCMOS. All right, now so there's kind of there's unstrained, and that's where all the layers have the same lattice constant. Okay, so that's pretty normal. I mean, your aluminum arsenide, gallium arsenide, you can keep growing as long as you want. There's single layer strained. And that's, for example, silicon, germanium, silicon. So everything is at the silicon lattice constant, including this. It doesn't want to be, but it's okay with it for as long as this isn't too thick. All right, and then there's a third, which is strain balance. And the example I'm going to give, because it's your homework, going back to our chart here. Okay. Now, if you look at this chart, what you'll see is that you can form an alloy between gallium arsenide and gallium phosphide. Meaning here it's all gallium phosphide, here it's all gallium arsenide. Now, one thing I want you to be aware of is that when you form alloys, it's not just the first atom that changes. Here the first atom stays the same. And when I go from gallium arsenide to indium arsenide, the group 3 atom is what's changing. When I go from gallium arsenide to gallium phosphide, it's the second atom, the group 5 atom, that's changing. So, you can grow strain balance, for example, where gallium arsenide is your substrate, and then you grow a layer of indium, gallium arsenide, and then a layer of gallium arsenide phosphide. And this one has a larger lattice constant than gallium arsenide, and this one has a smaller lattice constant than gallium arsenide. But if the sum of them has an effective lattice constant that's the same as gallium arsenide, it's happy. It's strain balanced, minus plus. And then you can keep doing this. Indium, gallium arsenide, gallium arsenide phosphide. Okay? And the homework today is evaluating that situation. And the homework is fairly self-explanatory, and you'll be able to figure it out. Okay, so those are the three main types of epitaxy. And other than that, in this section, I wanted you to, I should never do that. There's some pretty pictures in here. Again, most of the epitaxy done in research environments like our university is by molecular beam epitaxy, and that's all I want you to worry about here. It's fairly simple. Let's see what he has here as far as anything interesting otherwise. I mean, one thing to be aware of is that if you are, I think that's what he's talking about here. If you are growing layers like this, you can introduce dopant atoms into them as you grow them. So, for example, you can grow P-type material and N-type material. And so this is a way of making what's called an abrupt p-n junction. We'll talk about diffusion later in the course, but for example, I mean, you know, sort of a zero is homoepitaxy. I mean, these are forms of heteroepitaxy. Homoepitaxy would be, for example, to grow gallium arsenide N-type and gallium arsenide P-type. And so this is in a way of making an abrupt p-n junction, meaning it switches in basically a monolayer from N to P. So you can introduce dopant atoms at the same time you're growing, and that's, you know, pretty handy. Here's our silicon germanium. I think I asked you to look at including up to section 6.4. Oh, there's doping. Okay, that's why I did that. 6.4 is doping, and the point is that you can dope any layer however you want. Okay, and that's all I wanted to cover about epitaxy, and so, you know, the homework this week will let you have some fun with that. All right, now we're moving forward to starting to pattern devices, and so basically what we've learned are things like is how to put down layers. Okay, we've learned layers. You know, we've learned, you know, to, you know, like metal using evaporation. And we've learned about, you know, for example, silicon nitride using PECVD, and we've learned about silicon or silicon germanium crystals using epitaxy. You know, so these are, you know, these are amorphous or polycrystalline. And now we want to do patterning. Okay, and so the first thing that we're going to cover with patterning is essentially e-beam lithography, because that's how you start basically. See, if I were to write a book like this, I would do it how I'm teaching this, which again is to go through the processes first, and then circle back and talk about how to make, you know, recipes of certain devices. All right, so patterning basically means and I'm going to call it photoresist which basically means that if I have a wafer, I can put down a layer of photoresist, and then I can expose selectively. For example, I can come down with a exposure of lines, right? So I'm not telling you what I'm exposing yet. I'm just saying I'm using something. It could be a laser, it could be an electron beam. We'll go through that in a little bit. But basically, if I expose, I can make like a line where that photoresist is missing, or lines. Okay, so I can pattern the surface, and so I can make patterns in the surface that then I can do things like I could maybe then, like the lift off as we discussed, I can come down with metal and make lines of metal, or I could have had some other layer under here. I could use that as an etch mask. So there's various things I can do. And the word resist here basically means that it can act to resist whatever process you're doing next. So you form some pattern there, and like it's shown over there, you have some exposure pattern, and that gives you a pattern of resist that you can then use like a stencil, basically. And this is a nice picture here. Okay, here we go. Okay. I've learned that let me see if I can. Okay, it's kind of showing up better there. I've learned that I need to. Oops. I need to get rid of the sunlight in this room, or get a brighter projector. But okay, I'm not going to refer to the board so I don't mess up my focus. But this is what happens when you have so-called positive resist. Positive resist means wherever you've exposed it, the photoresist, that's this stuff, goes away. So for example, it's kind of like I drew on the board there. What I drew on the board is for positive resist. And so I have an exposure line, and then it goes away in what's called developer. There's a clean room video on lithography, and basically we'll be learning all about this. But we're just starting to get into this now, and I wanted to cover E-beam today. Positive resist, basically I have some exposure line, and then when I develop it, that photoresist goes away. Now, so what can I do here? Well, I can deposit metal in there and use a lift-off process. As we've discussed, if I deposit metal on this wafer, it goes down here in this trench. It also goes down on these surfaces here. But if I leave an exposed photoresist that solvent can get to, it can lift off all of that. Or if there was a layer, or I can use it to etch for example, a trench in my underlying substrate. If I use this photoresist as an etch mask, we'll talk about etching in a little while. Now, negative resist, it does the opposite. Where it's exposed, the resist stays, and in the developer, and everywhere else it goes away. Now, you can kind of get an idea that, for example, you see how these were, I believe, exposed with the same width exposure beam. So you can see that at positive resist, the trench is wider than a negative resist, the line is left there. And that's because in the development process, you tend to take away some photoresist more laterally beyond where the exposure line was. So you get the idea here that negative resist can be very, very handy because it can allow you to actually make finer features. So whether you use positive resist or negative resist, there's various reasons for and various processes, and we'll get to that as we go through this. But basically, this chapter is about doing exposure and photoresist. How does photoresist works? Well, I mean, he doesn't get into the chemistry here much, but you sort of just get the idea that when you take this photoresist, which is sort of a polymer material, that when you expose it to either light or electron beams, it changes its chemistry, and so it changes how it's affected in the developer. So you're performing a chemical change through the exposure, and that's all you really need to know about it right now. Now, specifically here, we wanted to go through electron beam lithography. And in electron beam lithography, you are placing a beam. So in this picture here, let me see if I can blow it up a little bit more. In this picture here, here's your electron beam, and here's your photoresist. And so if this were positive resist, basically where that beam went, you would be getting this trench after you do your development. Now, why is E-beam important? Well, it's important because using an electron beam, you can make very fine features. And there are laser writers Okay, so direct, right, lithography, so you can have a laser, where you basically bring down a laser beam on your, or you can have an electron beam. Now, if you've had any sort of physics on wave mechanics, well, it's really quantum mechanics, but you'll know, for example, that a laser, for example, a visible laser, has a wavelength of like a few hundred nanometers. Okay, that's the wavelength of a laser. And so that kind of, the wavelength limits how big your spot is. It's called the diffraction limit. And we'll talk a little bit more about that when we do optical lithography. But the point is that a laser has a large wavelength, and so it can only make very large spots using direct writing. And so people don't tend to use a laser, they tend to use an electron beam, because an electron beam has a very short wavelength, and so it makes a very tiny spot. Now, for those of you that are curious here about the physics of this, well, that's not the whole story. Okay, the wavelength of an electron and the beam's energies used here, it actually does not determine the width of the beam. All right, so first thing about electron beam is there is a beam width and then there is an effective, and let me forget the terminology he used here. Yeah, effective beam diameter. Beam, do you use width? Oh, spot size. Beam spot size. Okay. So if I have a wafer and I have my photoresist, the beam spot size refers to that, which I think he uses D for. But I won't write anything because I'm not sure what variable to use. But then there's an effective beam diameter. And that's wider than the beam spot size. And the reason why it's wider is given over here. All right. And now I'm not going to, he gives a few formulas here. I don't want you to get hung up on the formulas because they tend to be more useful for ratios. What I want you to understand is the physical process here. You can see from what I've drawn on the board, it's the same thing here. See, this is the beam diameter, and then the effective beam width is given by the scattering events that the electrons undergo in the photoresist. And so the effective beam diameter is wider, and it's based upon that scattering. And what this chart tells you is that the higher the energy of the beam, which sort of makes sense, the narrower the effective beam diameter in the photoresist is, because the electrons tend to go straight. Now, what you're primarily concerned with in an electron beam is the exposure time. And that's a function of what's called the sensitivity of the resist. So, let me find the formula here. See, this formula for D effective it's really more useful as a ratio, not. So this formula here, whether it's for a pixel or a whole wafer, there's something called S, which is the resist sensitivity. Okay, and the area you're exposing times the resist sensitivity divided by the beam current gives you how long it takes to do the exposure. So for example, and you can see basically S has units of tau I over A. Now you know what I is. I is charge per unit time. So this is coulombs per, and I think they usually use centimeter squared. So S tells you the charge in coulombs required to expose a certain area. And the beam current I then determines the speed, because tau goes 1 over I, of course, because the higher the beam current, the more charge you're bringing down into the surface. Now, I is not something you can raise indefinitely to make tau smaller, because the beam current is proportional to I. And that's where I was getting back to those of you that have taken quantum mechanics were probably thinking, oh, I can calculate that because I can calculate the quantum mechanical wavelength of an electron. But what's really happening here is that this beam width is governed by the repulsion between the electrons in the beam. And it just sort of works out that the higher the current, the wider the beam is going to be. So no, you can't just raise I to decrease the exposure time, because if you raise I too much, the beam gets too wide. Now, what else can you do? Well, you could increase the sensitivity of the resist. Now that doesn't work either, because if you increase the sensitivity resist, this is proportional to S. Meaning the higher the sensitivity, the wider that effective beam width is going to be. That's actually kind of an interesting question, why that is the case. And the reason why that's the case is because exposure is not, okay, so let's back up a little bit. This electron beam coming down are very high energy electrons. I don't know the exact conversion from 50 electron volts to the velocity, but they're high energy. Okay. In order to expose the resist, those electrons have to slow down. All right. Meaning it's necessary for them to undergo this scattering process in order for this exposure to happen, actually, because it sounds a little bit converse, but the higher the energy of the electron, the less likely it's actually going to produce a reaction on the molecule. So it has to slow down a little bit in order for that reaction to take place. So what happens is that if a resist is more sensitive, okay, that means you have a lower dose of electrons required. But what that does is that then with that lower dose, it actually causes, if you think about it, in order for you to get thermal electrons, they have to sort of laterally scatter even more. And so it's just basically a principle that the effective beam width, this is the resist, the effective beam width in the resist is proportional to the it's 1 over the sensitivity, sorry. So getting back to our formula there, tau, which is the one I want you to think about, okay, you can speed up the process by increasing the sensitivity, but then your effective beam diameter gets wider. And he has a, did I do that backwards? He has a little table over here with a few resists, and basically, as you can see, as the sensitivity, okay, all right, this is why I'm getting confused. All right, so I had it right the first time. So basically, yeah, no, 1 over S. Yeah. As the sensitivity goes up, all right, let's back this. Sensitivity is kind of, it's a bad word here. You would think that the higher the sensitivity, the less charge is required. But the way sensitivity is defined is it's the amount of charge required. And so sensitivity is kind of a misnomer here. I wouldn't know what I would call it if I were going to call it something different, but it's just the required charge, S, let's say. And so basically, if you, getting back to our, so S is the required charge. And let me so put sensitivity in quotes here, and it's really the required charge. All right, so let me walk through that again. The term sensitivity is the charge per unit area required to do an exposure. So the higher that number is, the more charge is required. So it sounds wrong because you think if it's more sensitive, it requires less charge. And so I never liked the word. So I just be aware, sensitivity is kind of anti that. It's how much charge you need. If it's more sensitive, it needs more charge. If there's a higher sensitivity, it needs more charge to work. All right, so in this table shows you that as sensitivity goes up, the feature goes down. Okay, which is the opposite of what you want, because getting back to our formula here, you see, I would like to make tau smaller, basically, so that it decreases the amount of write time required. I could increase my beam current to do that, but then my beam diameter gets bigger. I could decrease S, meaning it would require less charge, but as I decrease S, the effective beam diameter goes up. So what I'm getting at is you're not going to become experts in e-beam lithography from this short lesson. I want you to remember these few principles up on the board here. Okay, S is the resist and sensitivity in quotes, meaning the bigger it is, the more charge is required, and so the longer it takes. All right, as S goes bigger, it takes longer to do an exposure. And so a way to decrease the time is to make S smaller, but if you make S smaller, meaning it requires less charge, the effective line width goes up because it requires more thermalization of the electrons and spreads out. So this is what I want you to remember. I want you to remember that the beam spot size is proportional to I, the effective beam diameter is proportional to 1 over S, and the resist sensitivity is the required charge per unit area, and that tau is equal to AS over I. Okay? So I realize that's kind of a convoluted lesson, but this is what I want you to remember, and that's all I want you to remember about e-beam. It turns out that we do have an electron beam machine on campus. It's in Dr. Pereira's group, and they use it to do direct writing on photoresist to make features in their devices. But the main reason we're discussing it here is because it is the way masks are made. So this is a photograph of a 7-inch photomask, and you can see that it's a plate of glass with a layer of chromium. It could be other metals. I'll explain, well, okay, so we'll talk about that in a little bit. And basically, this mask was fabricated by, not by liftoff. This mask was fabricated so they had a plate of glass. They put down a layer of chromium, and then a layer of photoresist, and then they E-beam wrote, however, either with negative or positive to make openings, and then they put in an acid to etch away the chromium. And then, of course, they dissolved away the photoresist, and so they were left with these openings fabricated in the photomask. And the next lesson is on, we're going to get started on optical lithography, and you'll see what this photomask is used for. Basically, it's used to do a wide area pattern in one exposure, because you take your wafer, you take your photomask, with your metal features, and then you do an exposure on your wafer, basically using the photomask as an optical stencil. Now, what I've shown here is contact lithography. So this is your mask glass. So, lesson number 1, before we get started with optical lithography. Okay, you can, if you look at the your book, you can see, I think, that he's holding up the mask. Actually, I can't tell. The metal's on one side or the other. First lesson in the clean room, figure out what side of the glass the metal's on. That side goes next to your wafer. Because if you did it the reverse, the light would, go around the metal. Okay, so that's it. We finished on E-beam lithography. We've talked about photomasks, and now we're going to next lecture get started with optical lithography. Okay, that's it. Thank you.